Panie profesorze. No, w USAS-ie jesteś.
Okay, welcome. Welcome to the first seminar in this academic year at Warsaw University Observatory. My name is Pawel Pietrukowicz, and I will present the topic on the OGLE project. 30 years after the first microlensing event. And so we have many young people here, and I will have a quite broad introduction about the OGLE and also many scientific results I will report. OGLE, the acronym stands for the Optical Gravitational Lensing Experiment. And the idea of the of OGLE, of a massive photometric survey, was proposed by Professor Bogdan Paczyński of Princeton University. It was in his paper from 1986 when he proposed to monitor millions of stars of nearby galaxies, the Magellanic Clouds, in searches for microlensing events by observing for a couple of days at least, or weeks rather, months. And here what you see in the middle is a simple model of microlensing. So we have a source and the lens passing in front of the source, but here is the coordinate system reference is the lens. So the red point is the lens, and the green dot is the source in the background, and the green and blue are images, observed images, but everything is very, very small. These are micro arc seconds. And the changing surface of images results in changes of brightness. So what you see are changes in brightness characteristic for such a single lens, single source events. And there is also a parameter called Einstein time. This is a characteristic time scale of microlensing events. And on the right, you have a nice example of microlensing. This is not an example of gravitational lensing. This is not microlensing. This is a quasar lensed by a foreground galaxy, but this is almost ideal situation where you have the ring around the lens. So this is called the Einstein ring. Okay, and in the early 90s, it was not only possible to think about such a photometric survey, but also to try to conduct, to realize such an idea of massive surveys, and Poland open to the world, and it was with market economy easier to do something. And so in the early 90s, there was a proposal on the 1 meter swap telescope plus Campanas Observatory in Chile to observe the galactic bulge and also Magellanic Clouds. And the first night was April the 12th, 1992 for OGLE in general, but it wasn't a whole year devoted to observations, but only part of the year, and on other telescope, American one in this observatory. So there was an idea to build instrument and a telescope particularly devoted to observing to microlensing events. And in 1996, such telescope was finished, and OGLE started regular observations in January 1997. It was OGLE 2, on the 1.3 meter Warsaw telescope. And I'm mentioning only that there was also a break. There were phases I will show you in observations, unfortunately due to pandemic, but since last year we observe again. We are back to observations. And Las Campanas is located 500 about kilometers north of Santiago de Chile, and as you can see, it's clear skies, but I can tell you that over northern Chile, clear skies are almost every day, every night, which is very important for astronomers, and the weather is extremely stable. And the altitude of the observatory is about 2,300 meters, and the number of really good nights is really high, exceeding 300 nights per year, depending, of course, on the season. And I have to say that Las Campanas is, after Antarctica, the best astronomical location in terms of seeing conditions. So it's the median seeing is 0.6 of arc seconds. So observations of dense stellar fields are particularly good from Las Campanas. Oh, okay, I will mouse. Okay, and here you can see the OGLE telescope. The telescope is located in the top of the tower, 6 meters above the ground. Next to the tower is the control room, and from there the observations are conducted, and there is always an observer on the side. So we have about 3-week shifts in Chile. And we stay in this visitor observing mode all the time. The telescope is shown here. The primary mirror is 1.3 meter. Well, here it's remote, but of course the observer is in the control room. And as I said, now there are phases of OGLE. OGLE 1 was on the SWAP telescope. Starting from OGLE 2 was on the Warsaw 1.3 meter telescope. And every phase started with a new, larger camera, larger field of view. And of course, the number of stars increased every time. The amount of data increased every time. And currently, we observe about 3,600 square degrees of the sky. And in particular, the dense stellar fields, the galactic bulge, the galactic disk, and Magellanic clouds. So now we are in the OGLE phase since 2010. And the OGLE 4 camera consists of 32 CCDs and was designed by our PI, Professor Andrzej Udalski, and is cooled down to minus 115 degrees. We have space for 2 filters only because they are big, 30 by 30 centimeters. There is I-band filter and V-band filter, and what you can see here in the efficiency of the quantum efficiency of the camera. The field of view of the OGLE 4 camera is about 1.4 square degrees. So this is 7 times moon area, like shown here. And this is the sky we observe. So the galactic bulge, the whole galactic disk available from Las Campanas, and Magellanic clouds, so including the Magellanic bridge connecting the clouds. And time domain is the power of OGLE observations. This is an example of a star long period variable observed from almost the very beginning, and the last points are from the last week. And here at the bottom, I provide some rough numbers. So about 9,000 observing nights since early 90s. And in some directions, up to 20,000 exposures, 20,000 measurements in the I-band were taken. And this is the direction of the galactic bulge, the inner galactic bulge. Okay, now some history. So a few days ago, it was exactly September the 29th, 1993. The first microlensing event was announced. And this was a year after the beginning of OGLE observations, because in the first year, we had to prepare a base for bright measurements. And in this case, this first microlensing event, it was a star from galactic bulge lensed by a dwarf somewhere in the galactic disk. And since then, thousands of microlensing events have been detected. So, for example, in OGLE 4, before pandemic, it was over 16,000 such events. For comparison, I also show a number of lenses detected in selected years from other microlensing surveys. And on the right, you can see the picture of the galactic bulge with microlensing events. So this is over 1,300 detected until today, almost. So it's about 1,500, 2,000 events per year. And so I will go through some results. This microlensing observations were served for, in particular, solve the problem of dark matter. So the idea since the time, the paper of Paczynski, was that perhaps massive compact halo objects are the particles that form dark matter. But we quickly realized the number of microlensing events toward the Magellanic Clouds was very small. So after 12 years, it was really small number of events. And it showed that macho do not form dark matter, or in a very marginal way. And of course, not only solar mass objects were detected by a microlensing technique, but also planets. And the paper by Paczynski and Mao, already before the start of OGLE, indicated a possibility of detecting planets through microlensing. And this is the first planet detected in this technique. And here are on the left measurements taken by OGLE and also MOA. MOA is microlensing observations for astrophysics survey conducted from New Zealand. New Zealand is 9 hours after Chile, so we have data almost from 24 hours. And MOA was very lucky to catch the blue points from the peak where the planetary event happened. And on the right, you can see the parameters of the lens, so the star-planet system. And right now, since many years, we are using the so-called early warning system to detect any kind of microlensing events, including single, double, or even triple objects with planets, and not only. And here I show two more examples of microlensing. So in the upper part, you can see a Uranus-type planet. So this is a planet of 4 about Uranus mass detected on a white orbit. So this is this was first such planet detected, and it was detected with microlensing. And on the bottom, there is an example of a multiple system. So you have a binary star, and one of the components is orbited by a 2 Earth mass planet. So another example of detections, of planetary detections. And of course, since we have thousands of events, it's possible to say many things about populations in general in the galaxy. So, and one of the results is shown here. So in 10 years ago, there was we realized that there's so many planets in the galaxy, so at least one per star. And this was from microlensing, thanks to follow-up observations of the events detected by OGLE. And more or less same time, there was a paper about free-floating planets. So planets wandering through space without parent star. And from 10 events detected by the MOA survey, they claim that there are Jupiter mass planets somewhere in the space, and it was verified few years later by observations from OGLE 4, that there is no such large population. So the sample, of course, was much larger, and from Chile, the observations are much better than from New Zealand because of the weather. And so there are no free-floating Jupiter mass planets. This is the result of that study. And planets, OGLE searched not only through microlensing, but also transit techniques. And this was first planets discovered with this technique, and 7 planets were confirmed. And I will show you that recently we have many more candidates. And another topic is cosmic distance ladder. So thanks to detection of thousands of variable stars of very important types, like classical civets, Lyrae stars, and also eclipsing binaries, it is possible to measure distances with better accuracy, for example, to the Large Magellanic Cloud. And of course, for this are very useful the period luminosity relations. So on the right, you can see almost all classical civets detected in the Magellanic system, almost 10,000 objects. So work finished, the work that started by Henryka Hivik was finished. And one more thing, so if you have really thousands of stars, there are some very important exceptions, and one of them were very really few civets in binary systems, and this is an example. Was a star eclipsed by another giant object, and thanks to spectroscopic additional observations, it was possible to measure the mass, and the mass turned out to be predicted correctly by the pulsation theory. So in comparison to evolutionary predictions, so this was correct from pulsation models. And So OGLE 4 has this a large field of view, and it turned to be, since 2010, a wide field survey. So it was possible to observe more. But even in the early years, some results on the whole structure of the galaxy were done. And this is the first example. So in 1993, 1994, from OGLE 1, the observations of red clump giants showed that we have a bar, and this was the final evidence for the that our Milky Way is a barred spiral. And we have old stars, we have intermediate age stars, young stars, and our Lyrae stars are very old, more than giga years old. And here you can see over 40,000 Lyrae stars detected in the inner galactic bulge in the optical by OGLE. In the optical, so you can see that very close to the plane, we cannot see anything. And the stars were used to trace the structure of the old galactic bulge, which turned out to have the shape of a triaxial ellipsoid. So here you have the numbers, and the ellipsoid is inclined with the angle same as almost the same as the bar with respect to the line of sight from the sun to the galactic center. So here you can see again this. Okay. And now about the young population. So you can see the disk, and so thanks to covering the whole disk, it was possible to discover almost 2,000 Cepheids, classical Cepheids, and to trace the true shape of the young thin disk. And here is the result. So this is the first such detailed map of our galaxy, because the distance were measured individually to each star, and there are no assumptions. For example, in the radio maps, there were assumptions on rotations, and here with our maps there is no assumption. Another thing is that for the first time we were able to see the shape on the outer part of the disk, and we showed that the disk is warped. So this was the confirmation, and is flared. Of course, in the background, the image is a galaxy, not our. And so observations of millions of stars allowed the detection of many interesting things, completely unexpected objects, like, for example, the blue large amplitude pulsators. So the stars that pulsate very quickly, this is half an hour, more or less, with large amplitude. So imagine our sun, or imagine a star which is about 70% of our star, but you can imagine our sun that changes, changing the brightness by 40% in half an hour. So this is really quickly with huge amplitude. And the formation of blobs are unknown. And here is a comparison of sizes of various pulsating stars, including blobs and Lyrae stars. So here are the prototypes of the stars. So as you can see, our Lyraes are 5 times larger than the sun. Delta Cephei is 40 times the size of the sun. Beta Cephei is the same size as our Lyrae star, and this is a main sequence. And Myra is about 400 times the sun, twice of the sun. Another very, very interesting object was a red nova. So there is a few red nova detected at all in the history. On the left in the image, you have Nova Monocerotis observed with Hubble Space Telescope. So it was over 20 years ago. And in 2008, there was a explosion, nova explosion, which was classified to red nova. And thanks to OGLE observations before the explosion, it was possible to solve the mystery of such objects. So for comparison, classical nova are not red, they are blue, but these objects, the red nova, were redder and redder in time. And here you can see what happened before the explosion. So it was an eclipsing binary system that merged or underwent a common envelope phase. And now the object is fading, but there are no two stars. There is one. There is one atmosphere. And from cosmology, so in the background of Magellanic clouds, we observed many galaxies and exploding supernova of various types and tidal disruption events, about 200 per year. And here I show you that some objects, so the quasars were confirmed with spectroscopic observations from Anglo-Australian telescope. And finally, there are really few objects we observe outside the galactic bulge, the galactic disk and Magellanic clouds. And this is the Einstein cross or Hooke's lens. And you can see the HST image at the bottom and the OGLE images middle and top. It's the same image, but different brightness sets. And what we are doing for over 20 years is the monitoring the precise brightness measurements of the 4 images of this quasar. Okay, and now let's go to last year. So OGLE after pandemic. So there was a 2.5 year break in observations. And in last July, August, there was a engineering mission to the telescope to recover the telescope and to return to regular observations. And I have some pictures. So it was winter time, and it was a lot of dust to remove, to clean. So several days have to be spent on cleaning, washing the instruments. And also inside the electronics and the mirror. The mirror was dirty, as you can see. So dust is generally a problem there, but in the desert. But this year in May there was a aluminization. So another engineering mission, but this time not only primary but also secondary mirror were removed. So here you can see the secondary mirror in a wooden case on the way down in the tower. So this is the primary mirror before washing. So it was transported to the nearby DuPont telescope, which is in the background. So this is a picture from the OGLE tower. And both mirrors were put into washed first, yeah, by the Las Campanas staff. And both mirrors, as you can see, this is pure glass here, were put in the vacuum chamber. And after a day, you can see the new coating. And again, were installed in the telescope. And two more pictures. So the filters again, and the camera were attached, and the observations are back. Okay, and there is one more thing on the side. So we have asphalt on this road, and from my experience, because I was there in July, is that there is less dust now, thanks to this asphalt. The asphalt was put because there is another project on that location conducted. Okay, and so this is our website, where are the details, well, on the telescope and the data on the variable stars. So the OGLE collection of variable stars is there. And also, I'm not showing this on the left, there is the real-time data analysis system. So this is not only for microlensing, but also for X-ray sources. I mean, the optical counterparts to various X-ray sources, and NOVA, etc. Okay, and now the most recent results. So we've detected thousands of Mira stars. Mira stars are intermediate age giants, and we see them in the whole galaxy, also Magellanic Clouds. And this is the map we obtained with Mira stars, and with this we confirmed the shape of the inner part, the bulge, and also the shape of the disk, so the flaring of the disk. Delta Scuti stars, another type of variables, they are everywhere, and the bulge disk, Magellanic Clouds everywhere. Here are the examples. This is a really huge variety of the shapes of those stars. They are single mode, double mode, triple mode, or multiple mode, many modes. And the map of the bulge and the disk is on the left, lower left, and the lower right are Delta Scutis from the Magellanic Clouds in a period luminosity diagram. So you see two sequences. The upper sequence is from first overtone pulsators, and the lower is from fundamental mode pulsators. So for the first time, we see two sequences separate from each other. And Delta Scutis from the bulge. So for me, it was a bit strange that I expected that Delta Scuti are general population 1 stars, and S6 Phoenicis are population 2 stars. So I expected that I will see two separate groups, but nothing like that. And there is only one uniform bulge population, and this was also confirmed with models for triple mode stars on the right side. So you can see a continuous sequence and the continuous scale in metallicity and also age of the stars. Okay, and other types of stars quite recently discovered. About 1,000 heartbeat stars. Heartbeat stars are binary stars with components on elliptical orbits. So the changes, the variations in brightness are large when the components are close to each other. And finally, new blobs. So about 20 new objects in the galactic disk, and also other stars on the short period stars on the right. And one of the stars, the bottom left, is the shortest period variable ever detected in the OGLE data. So this is only 8.5 million. Okay, and we started with microlensing, so I will finish with microlensing. And there was an event in 2011. It was a high magnification event, as you can see, over 3 magnitude, and quite long. So the time scale here is about 5 months. Usually the events are much shorter, a few days. And it was observed also from the Hubble Space Telescope. So in the bottom, you see astrometric measurements from HST and results of analysis done by two groups, and the final numbers of the lensed object. So it turned out to be an isolated, free-floating black hole, about 8 solar mass, located about 1.5 kiloparsecs from us. So such first object detected with microlensing, and the first isolated black hole in general, a stellar mass black hole. And something which is in preparation. So we merged observations from OGLE-3 and OGLE-4 for Magellanic Clouds. Here, for the large Magellanic Clouds, to look for really long time scale events from black holes, massive black holes, somewhere in the halo between us and the clouds. But as you can see, the result is negative. I mean, that the number of events is very, very small, despite the huge number of millions of stars observed by OGLE in the cloud and the LMC. And so the 18 cases, the 18 events can be explained by either objects observed in the halo, but there are a few of them, or self-lensing, so by stars in the LMC. So the lensed objects are in the LMC. And the small number is the evidence that we don't have black holes in this given range here. Okay, and the last slide, planets. So in the bulge, we have about 100 candidates for transiting planet this time. And this time was used a sophisticated technique to detect transit, because in the early 2000s, simple transits were searched for, and some of them were eclipsing stars. But here, not only OGLE data were used, but also data from Gaia and from other surveys, measurements, color measurements, to indicate the transits of planetary nature. So as you can see in the bottom, the planets are somewhere, because so the fields were observed toward the galactic bulge. but the planets, the stars with the planets are somewhere in the galactic disk between 1 and 6 kiloparsecs from us. Those are the red points. And for comparison, there are other other known planets in gray here. Okay, so that's it. Thank you. I can take questions if you have here.
Widzisz go na Zoomie? Okay, someone from Zoom, Sud Hagar, can you?
Hi, thank you for your nice presentation. I have a very naive question. Is there any theoretical estimation for how many number of microlensing event can detect by OGLE in each observation cycle?
Could you repeat again, please? How many?
How many events we can detect from OGLE observation? Is there any theoretical prediction for each observation cycle or each candidates, like supernova or cepheids or planets?
Microlensing events of
in the galactic bulge per season, we can detect between 1,000 and 2,000 microlensing events per year, but in the Magellanic Clouds it's 10 times less, or no, 100 times less. It's about one or few events per year towards Magellanic Clouds.
Okay, thank you.
Thousands to one towards the bulge.
Yeah, I showed it. Yes.
You mentioned that you will detect 18 lighting events toward clouds or toward large Magellanic. Too small or too bold?
No, only the large one.
Large.
Yeah, because the database, the data were merged for the LMC only, I think, right now, yes.
Yeah, so it's throughout last 20 years, we detected like 17 or so events towards large Magellanic Clouds, but we haven't yet checked in such a rigorous way the data from small Magellanic Clouds.
And what is the approximate number of stars observed above?
SMC, 2 million only, in comparison to 80 million. Not much.
15 million.
And one thing to add to this picture is that all of those 17 microlensing events throughout last 20 years are consistent with being lenses from our galactic disk or the Large Magellanic Cloud disk. And there is no candidate for anything in between. So that's why the model here, the strict model, is assuming that no primordial black holes lenses were observed, because we don't believe that any of those were not from either Milky Way disk or the LMC disk.
But from Łukasz Berzykowski's work, it was about 6 and 5. No?
Yeah, after 12 years, yes. But we revised them, and some of them were, in fact, no microlensing events, I think.
I don't remember.
Yeah, because you know, if you observe for many years, then you are sure that the event that happened was unique. So 18.
Okay, so, but in this analysis, you assume that the single black hole towards the galactic center, that it's of stellar origin, that it's not primordial.
Of stellar, yes.
This one.
Yes.
And is there a reason why you assume that, or? Because I don't think it's later.
There's a 8 solar mass and the galactic disk. We expect
Okay, but do you expect also this solar mass? You are looking for such black hole masses as primordial ones. I mean, you want to add the head. And another question is, you will continue observing. So, what are the questions, challenges that you think you will answer over the next year with more data?
Yeah. Okay. Well, this is
What should I expect for this talk next year?
Well, we will concentrate on rather on transient events, but we will keep observing the galactic bulge and the galactic disk, the dense area of the sky. So I think the future is observing. I mean, near future is observing transient still. Yes, transient, because the many periodic stars are known right now. So I think still that there are unique objects or objects that we don't know are well, this is a tough question, actually. Yeah. So one of the ideas is to we have in next year to change the filters in or at least one of the filters. And so maybe you help me.
Yeah, so we also changed the cadence for observing microlensing. If you go back to this plot for dark matter from LMC microlensing,
In the beginning.
So the exclusion, why we don't expect primordial black holes. This is because we don't see them toward LMC. We don't see lensing, and our limits are very strict. However, there is a mass component to them.
Which one? Okay. Yes.
There is a mass component to them. We are not sensitive to very light primordial black holes. So if we move the cadence to a very short one, then we will be sensitive to the very light machos. Like we will extend this this exclusion zone we can extend to masses below 10⁻³ solar masses, going to the planetary masses as well. We have a question from Zoom. Łukasz?
Yes, I hope you can hear me. Hello, very nice overview, Pawel, thank you. I just wanted to ask, has anything changed in terms of plans for releasing at least portions of the OGLE data, especially the old ones, even the images and especially the catalogs that would be extremely valuable for research? For example, for the LSST people designing the survey, that would be extremely helpful. Are there any plans on releasing the data?
Well, at the moment, so we are releasing only the products. So I don't know, maybe OGLE-free will be released, the data, but not the recent data. But of course, all the transients are online. Yes. So every new point is there on the web page.
Okay, thanks.
Can we add something?
Okay, we don't see any more questions.
Okay, more questions here?
Okay.
Okay. Zostało zatrzymane, tak?
Nie.
Zostało zatrzymane.
Tego się nie da.
Nie, no musi się dać, bo normalnie tego nie było.